Hello and welcome to this tutorial on power flow in the induction machine. I'm going to be looking at this from the perspective of the induction machine operating as a motor as opposed to it operating as a generator, which it can do. The principles are basically the same, everything is just reversed in terms of the way that we look at it, and I'll talk about a little bit of that later on. But first of all, in order to understand how the power flows in an induction machine, it's often good to just revisit what the induction machine actually is, because when you're sitting in the exam and you can't remember some of these equations, if you remember what's actually going on, then it's much easier. You can go back to first principles, as an old teacher of mine always used to say. So if we remember that the induction machine has got 6 poles, 3-phase induction machine that is, and they are basically like this. And I'll make an attempt to move this into 3D. And each of these poles has got windings around it. Like that, and we'll call these A, B, C, A dash, B dash, and C dash, because these two are configured together, these two are configured together, and these two are configured together. And when we apply a 3-phase waveform to this, we get our rotating flux field. Inside there, we have our rotor. And that's going to be spinning, and coming out of there is a shaft. And at this point, I'll just change to the blue. So here's our shaft coming out, and our shaft is going to be spinning. It will have a rotational speed, and it will be able to deliver a torque, and that is our mechanical output power. Our electrical input power that's going into this is √3 voltage, current, and power factor. So we've got, there's our power going in, there's our power coming out. As the power goes through here, we're going to be losing it. We're going to be putting this electrical power into these wires. These wires have resistance, therefore there will be an I²R loss there. The core here is made of laminated material, so therefore there will be eddy currents and various things like that, and hysteresis losses and all of those sorts of things going on. The rotor is made of typically aluminium, with lamination, so again that will have a resistance in the rotor, and also the impedance is associated with that. This whole rotor and shaft is sitting on a set of bearings. We can sort of pretend we can draw some bearings here like that. These bearings will have a resistance, so there's power loss there. So all through the process, as the power flows in, we're losing little bits of power all the way through. And the way that this is often explained is through a visual power flow diagram, which is something that I found very helpful, because I'm a visual person and I like if things are laid out visually for me, I find it much easier to follow. So what we're going to do is we'll start here with a diagram that shows the input power coming in and then moving this way towards we get our output power over here. And as we're doing that, various powers are going to be lost and manifest itself as heat through here. For example, the I²R losses in the rotor and in the stator, and all these other sort of the windage losses and all of that sort of stuff. So if we draw that out, we start off here, we'll come down here, we'll give ourselves plenty of room. This here is our input power, and we've explained what that is. The first place we're going to lose power when we come into these windings, the first place we're going to lose power is in the resistance of those windings. And so that is often called the power loss in the stator through copper, PSCU. And that can be found pretty straightforward. It's 3 times the current squared in the rotor times the resistance, the copper resistances. And so that will give us our first power loss there. once we've got the power through these windings, we need to get it into the core here. So we're going to have another power loss here. And this one here is called the power loss on the core. And that is 3 times the current in the core times the resistance of the core. That gives us our power through our primary to our air gap here. And that's what this power here is called. It's called the power in the air gap. And it can be found, there's an expression for finding that, which is 3 times the current in the secondary squared times the resistance of the secondary squared over the slip. These terms here, with these dashes and all of that sort of stuff, these terms come from the induction machine equivalent model. They aren't, for lack of a better term, a real value. They are values that have been derived from the equivalent circuit, and I will be putting up a tutorial on the induction machine equivalent circuit. If it hasn't gone up before this one, it'll be going up after it. It will be there. So, we now have the power in the air gap. What we then have to do is get that power into our rotor. And in doing so, the power that's in the rotor, again, we experience a loss of power here. There's some power that's lost here. And this power here is called the power that's lost in the rotor because of the copper. The resistances are there. And that is found by 3 I squared R2. It is also equal to the slip times the power in the air gap. Once we've lost the power through the rotor here, we now have what some people would call the mechanical power, but it's not. The proper term that's used to describe the power at this point here is the converted power. And in some books it's also called the power in the electromagnetic power. This is the power that's present in the shaft, but we've still got a few more losses to do before we can actually get it out. And those losses are the losses through to friction and windage, and also there'll be some stray losses as well. As an aside, and back to the equivalent circuit, this power here can be found by 3 I2 squared R2 1 minus the slip. Now, once we've taken care of the losses through the ball bearings here and the fan and whatever stray losses that might be floating around that someone's forgotten to include earlier, that is our output power. This is our mechanical power that we actually get out here. If this was an induction machine, we would consider it the other way. We would have a mechanical power subject to stray losses, subject to friction. We would still have a converted loss, which would then we'd lose more here in the rotor copper losses, which would have, then we get our power into the air gap, and then we'd lose power in the stator, and we'd finally have an electrical power coming out. If it was acting as a generator, obviously our electric power out will be less than our mechanical power in, so the flow of these arrows would be different, but the same process still applies, just in reverse. So let's go through a simple numerical example just to cement this in. Let's say we've got a 3-phase 50 horsepower machine. It's rated at 60 Hertz, 480 volts, and it's drawing 60 amps with a power factor of 0.85, which is all quite reasonable. And let's also say that we know these values through here. So we'll say that the power in the stator copper loss is 2 kilowatts. The power in the rotor copper is 0.7 kilowatts. We'll say friction and windage is 0.6 kilowatts. The power in the core is 1.8 kilowatts. And we haven't accounted for the stray, but we'll say that that's negligible. So first off, we're looking at this and we can see that we're already losing 2 kilowatts here and 1.8 here. So we're losing almost 4 kilowatts in the stator windings of this machine. Out of 4 kilowatts, that's a lot of energy. We're going to have to seriously think about how we're going to cool this machine. It would need fans on it to keep it cool, or some form of something going on there. It's a lot of energy to be lost. So if we want to understand what the input power is, what the power is in the air gap and all this sort of stuff, and find out the efficiency of this machine, we need to go through and find out all these values. So the electrical input power, as I've said, is root 3 times the voltage times current times the power factor, and that is root 3 times 480 times 60 times 0.85, which is 42.4 kilowatts. Just go back to my previous comment, these two here add up to almost 4 kilowatts. We're putting 42 kilowatts in, so we can already see we're losing 10% of the energy that we're putting into this thing in the stator. This is not, this is significant and needs to be addressed. So we now know the input power. We can figure out the power in the air gap, which is the power in the air gap is simply this power minus these two powers. So the power in the air gap is the input power minus the power in the stator copper losses minus the power in the core, which is 42.4 minus 2 minus, where is it, down here, 1.8, and that equals 38.6 kilowatts. So we now have the power in the air gap. We can find out the power that's converted, which, as I've said, is also called the electromagnetic power in some books, and that is the power in the air gap minus the power of the rotor copper losses, which is 38.6 minus 0.7, which gives us 37.9 kilowatts. So we've now got this power here. It's converted, it's at the shaft, it's been converted, and we've now got a few losses to take care of before we can get the output power. So the output power is our converted power minus our friction and windage losses minus our stray losses, which is 37.9 minus 0.6 minus 0, which gives us 37.3 kilowatts. As an aside, we could convert that into horsepower by dividing it by 0.746, and that would come out to being 50 horsepower, which is what we knew anyway, because that's what the question told us in the machine. So we could have found out the output power in kilowatts and then added these two to it. Well, this one's 0, added this one to it to got that, and then added this to get that. We could have gone back the other way. It's simple algebra, simple addition and subtraction as you flow through. So now we have the output power, we have the input power. We can find the efficiency of this machine. power out over power in, which is output power is 37.3, input power is 42.4, and that gives us an efficiency of 88%. And we can tell almost all of this is being lost here in this data. Marginally smaller bits down here in friction and through here, but the majority of it is lost up here in this data. This is why so much effort goes into data design. That's all we've got for today. A reminder that the equivalent circuit tutorial will be going up in due course. And on that note, I'd like to say thank you for watching. I look forward to seeing you again. Thank you very much.